Okay, welcome again to lesson 2 of my physics playlist. And today we'll be talking about vector addition. Now, last week we talked, just a quick recap of last week's lesson. We were talking about we were defining what a vector really is. So, once again, let's recap that. A vector is a quantity, n, which has a magnitude and also has a direction. And that is the counterpart to a scalar, which is also a quantity and has a magnitude too. However, it does not have a direction. So that was what we talked about last week. And examples of a vector would be like displacement, velocity. Examples of scalars would be mass, temperature, speed, and distance. Okay, so let's just keep this little definition at the very top here, if I can fit it somewhere. Hold on. Let me make some room. Okay, there we go. So let's put it at the very top here just to keep the definition in mind of what a vector is. Okay, so how do we add vectors? When we think about addition, what do we think of? We think of, like, let's say, what is 1 plus 3? We would think 4. However, this is not always true. This is true sometimes for vectors, but this is not always true. Now, I'm going to show you a case where this is true. Okay, I'm going to just put it at the side here once again. So, when is this true? Okay, so let's say we have a vector, and now a vector can be represented by arrows. So let's say that this is a vector, and we shall call this vector vector A. And now, just a quick little side note. When we're dealing with vectors, the notation that we use, we don't just say A, because A can also represent a scalar. In order to differentiate a variable, a scalar variable from a vector variable, we add a little hat on the top, the arrow hat. Now, this can be half an arrow or a whole arrow, and it used to be the whole arrow, but physicists just got lazy and just took away half of it. So yeah, so I prefer to use the half arrow. Or in textbooks, you'll see this being used. A bold and italicized a or variable means it's a vector. But since we can bold out or italicize our words, our hand-drawn letters, not me anyway, we use the arrow. So let's say that this arrow represents vector A, and let's say this has magnitude of magnitude 1. Okay, and let's say we have another vector. So I'm just gonna copy this arrow. Let's say we have another vector, and we're gonna call this vector B, and we're gonna say that it has a magnitude of magnitude 3, just like the like problem above, this addition above. So, well, I'm not going to care about units right now. I'm just gonna say that it has magnitude 3, just as an abstract thing. So, and I almost forgot the arrowhead. So, A is 1. I should probably write that down here. A equals 1. Okay, there we go. And then we have a random floating 1 around here. Let's take that away. Okay, so there's something wrong with this diagram still. If vector A has magnitude 1 and vector B has magnitude 3, their arrows cannot have the same length because it doesn't make sense. If a vector has a magnitude that's greater than another vector, its length should be longer than the other one. So let's cut this short. Let's just take away. Let's make you short. Oh, he looks so short now. Anyway, so this is vector A, and he has magnitude of 1, just like this one. Now, how do we add vector A to vector B? How do we do that? Very simple. The rule for addition, I'm going to write it down here. So the rule for addition is to place the tail of one vector on top of the head. I'm gonna bold that. I'm gonna bold that letter. I mean that word. Oh, whoops! No, that bold the whole thing. Oh man, paint sucks. Anyway, on top of the head of the other vector, if there is only two, and we'll deal with multiple vectors later on. But for now, we're just going to be dealing with two vectors. So we will place a tail. Place a tail. No, yeah, it still doesn't do that. Okay, so we'll place a tail of one vector on top of the head of the other vector, and then the sum of the vectors, or we'll call it, or also known as the resultant or net vector, is the arrow or vector, I guess, that is drawn from the start to the end, quite simply. So the start meaning the tail of the first to the head of the second, which I'll show in a moment here. So what did the rule say? So we're going to place a tail of one vector on top of the head of the other vector. So let's just choose one vector. It does not matter which vector you choose first, like which vector's tail to put to which vector's head. It doesn't matter, as I'll show in a moment. So let's say we choose vector A as the one to put on. So what the rules say? Place the tail. Now, where's the tail? Obviously, this is the arrowhead, so this has to be the tail. So place the tail. I'm gonna try this. Place the tail on top of. So, oh man, paint cuts it off. But anyway, so we're gonna place it on top of the head of the other vector. And what did it say next? The sum, so to the addition of the two vectors, also called the resultant, is the vector that is drawn from the start to the end. And I'll show that right now. Okay, so here is an example. So Bob travels 3 kilometers north and another 1 kilometers north. And what is his total displacement? So let's use this diagram. Let's say, and we also need a reference. We always need a reference, like where is north. So we're going to say that north is in the up direction, because it just makes sense. So that's north. So this, I've made it so that the question deals ties in exactly with the vector diagram. So Bob traveled 3 kilometers north, as shown by vector B, and 1 kilometer north, shown by vector A. And when we want to find the displacement, we add both vectors together. And I'm going to talk about displacement later on in kinematics, which will be down the road. But for now, it will suffice to say that displacement is just the addition of these two vectors. So we're adding A and B together and to find displacement. So how do we add vectors together? As said in this rule for addition, all we need to do is place a tail of one vector on top of the head of the other vector, as we did, and then the sum of that will be an arrow drawn from the start to the end, and I'm going to do that right now. So from the start to the end, simple as that. But now you can't really see that, so I'm gonna erase this and draw it by the side. So from the start to the end, and let's just say that these two lines are parallel, so that it's parallel here, okay? And let's just pretend it's parallel. And the thing is, we don't want to draw the arrowhead directly at the end, because it will be confusing, and people will confuse it with an actual vector. And as I said earlier, the resultant isn't really a vector. It isn't one of, like this vector, like this long vector isn't exactly the 3 kilometers or the 1 kilometer that I was stated in the question. It just represents the net displacement or the total displacement. So it's not actually a vector in the sense that it is not part of the question. So in order to differentiate this vector from the actual vectors that are part of the question, we need to find a way to differentiate that. And the way to do this is not use the arrowheads, but draw 2 arrowheads in the body of the vector, like that. And that will tell the reader that this line is the resultant. So in this case, when you add the two vectors together, the answer, like the resultant, the magnitude would just simply be 1 plus 3, because both of them act in the same direction. So we're just adding 3 plus the 1, because this arrow stands for 1, length 1, and length 3. So the total displacement, or the red arrow, the length of the red arrow would be 3 plus 1, which equals 4. And this is the only case where normal addition will work. Only if the 2 arrows, or how many arrows you have, act in the same direction in a straight line. So all arrows are parallel, like north, and all are positive. So basically not south, just all north. Subtraction will do that later, but for now, 3 plus 1 equals 4 only works if the arrows of the vectors work and act in the same direction, and they're all linear. So 4 kilometers what? We need to write down 4 watt, 4 kilometers, and we need direction, which is north. As you can see in the diagram, the arrow points north, as said by this. Since it points up and north is up, the direction is north. And this is the easiest problem you can get in vectors, dealing with vectors, where normal mathematical addition rules apply. And in the next tutorial, I'll be talking about adding vector addition in the second dimension, so 2 dimensions. So not just linear, but sideways as well, and angles and all that kind of stuff. So yep, that's about it for this episode, our lesson. So until next episode, guys, I'll see you then. Peace out.